Hello and welcome to the Titus Timeout podcast. I'm Jenny Abney-Civey, and this week I want to continue with our discussion about altitude and talk about selecting fans at high altitudes. If we go back a couple podcasts ago, you might remember my drawing of the 1 by 1 by 1 foot cube of air in Dallas compared to the 1 by 1 by 1 foot cube of air in Denver. And you might remember this awesome drawing of the United States I did. Since the air pressure is lower in Denver, there's basically less stuff in the box of air than there is in the box of air in Dallas. So it's the same cubic foot of air, but there's less stuff in it because there's lower density air at higher altitudes. And because of this, the heat transfer abilities are lower at higher altitudes. So that kind of sets up where we were. Let's move this out of the way and let's look at what does this mean for fan selections. So a fan is a constant volume device. This means at a given rotational speed, a given RPM, it will move a specific volume of air, a specific CFM. So let me draw a forward curve fan wheel. There's a couple blades in here. So that's our wheel. Let's say each one of these blades can hold or essentially move 1 cubic foot of, we'll call it air, but it could be whatever. Imagine a scoop just coming around and pushing that much air forward. So if each one of these holds 1 cubic foot, there's 7 of them. So if this went 1 rotation per minute or 1 RPM, that would basically be 7 cubic feet of air every time it rotated once, or 7 CFM because it took a minute to do it. So our very, very slow fan here is moving, but you can see how it doesn't really matter what's in it, if it's air or if it's water. If every time it makes 1 rotation, it moves 7 cubic feet of whatever fluid it's moving. You can also imagine that if it was moving water, it would be harder to rotate the fan. So this is exactly what happens with air at high altitudes versus air at sea level. I make a little bit of room here. So at high altitudes, it's like the air versus the water. It requires a lower horsepower because it takes less effort to move it 1 rotation. Now air and water are kind of extreme as an example, but I think it helps make the concept a little more obvious. Static pressure is also affected by altitude because there's less mass to the air at high altitudes at a given CFM of airflow. It'll generate less static pressure as well. The density goes down, the static pressure goes down. So if I go back to my original example from the first podcast on altitude where I talked about the rocks and the feathers, it's not hard to see that if you had a cubic foot box of feathers and a cubic foot box of rocks, you'd feel a lot more pressure from the box of rocks, say if someone accidentally put it on your foot. So let's look at selecting fans that will operate at altitude using catalog data that are based on standard air. So to do that, the first thing you need to do is convert your actual air operating points to the standard air equivalents. To do that, you need to first determine the air density ratio. The air density ratio is equal to the actual air density divided by the standard air density. So if you use somewhere like Denver, where the air density is around 0.06 pounds per cubic foot, you would get 0.06 divided by 0.075, which is the density of standard air, and that equals 0.8. So I also showed you in a previous podcast that there are correction factor tables for various densities and temperatures. So remember that we're only talking about altitude here, but temperature affects density as well. So I showed this one in the standard air podcast from a couple weeks ago, and you can see right here at 6,000 feet is 0.8. Okay, so I make a little more room again. Now a CFM is a CFM, and an RPM is an RPM regardless of your altitude. So let's put this here. CFM standard air and CFM actual are equal, and RPM standard air and RPM actual are equal. So let's say we want to pick a fan that is 5,000 CFM at 2 inches. And now we have our air density ratio of 0.8 up here, which we're going to call Denver. So the static pressure at altitude needs to be converted to the static pressure of standard air. And you get that by multiplying the static pressure at altitude that you need, this 2 inches, by 0.8, our air density ratio. So 2 times 0.8 equals 2.5 inches of pressure. So now you would select your fan based on manufacturer's data, based on your 5,000 CFM and 2.5 inches. And this will allow you to select your fan and get the RPM you need to get the airflow out of your fan you need. So again, let's make a little bit of room. And I'm going to draw in a fan curve. So down here we have CFM, up here static pressure, and our curve will look something like this. And then let's just call this point our 5,000 CFM at 2.5 inches, and we'll say this RPM curve is 1,500 RPM. Now let's add in a horsepower curve right here. And we're going to take our line right to there, and let's call this 6 horsepower. So based on standard air, our fan that we've selected has a brake horsepower requirement of 6 horsepower. So now we're going to take our 0.8 air density ratio and multiply it by the standard air horsepower that we got off our graph. So 0.8 times 6 equals 4.8 is our brake horsepower for our fan at our altitude up here in Denver. So to kind of summarize, you take your requirement, 5,000 CFM at 2 inches, but since you're up at altitude, you need to use the air density ratio to correct your static pressure. So you'll take your 2 inches and convert that to 2.5 inches at standard air, and that is what you use on your manufacturer's data chart to find the fan that works for your operating points. From there, you know the RPM of your fan, which will give you the horsepower as well, and then you use your air density ratio again to calculate the brake horsepower for your location up here in Denver. So now you see how altitude affects fan operation and selection. Don't forget to subscribe to our YouTube channel, and thanks for taking a time out with us.